Okay, onward to triple integrals. Okay, in triple integrals we have two coordinate systems. We'll look at both of them separately. The first one is cylindrical coordinates, and then we'll go on to spherical coordinates. Cylindrical coordinates are really just a three-dimensional extension of polar coordinates. All right, in cylindrical coordinates you just change your x and your y into polar, and z stays z. So if I have a point in the xyz coordinate system, maybe it's out here. I think about that, dropping that down in the xy plane. Here's my r, here's my theta. So x is still r times cosine theta. And y is still r sine theta. And z is just z. Okay, so here's my x, and you can see from this triangle, x is r cosine theta. Here's my y, or you can think of this as being my y, r sine theta, just like before, and z is z. Let's do an example. So in cylindrical coordinates, find the volume bounded by these two shapes. Okay, so I need to know what these shapes look like first of all. And z equals 50 minus x squared minus y squared is a little upside down paraboloid. And z equals x squared plus y squared is a little right side up paraboloid. So if I try to draw these guys, this is at 50, and it comes down. And then I've got another one at 0, and it comes up, and they're going to hit. Okay, so it's bounded by those two shapes. It's also outside this cylinder, so that's easy. X squared plus y squared equals 1. That's going to be this guy here in the middle. So this looks like a bead. Okay, I got a shape that comes around like this, and it's got that hole drilled out of it in the middle. Okay. This is something that I can't do in rectangular coordinates because of that hole in the middle. It's just a mess if I try to do that, but I can do it in cylindrical coordinates really easily. And in general, cylindrical coordinates are nice when you have something that has like one circular cross-section, but it has like an axis of symmetry, which this one does. We've got this beautiful axis of symmetry on the z-axis, and then everything around in the xy direction is round, which is really nice. Okay, so let's see what we can do. It's a volume, so I'm going to integrate 1. All right, and in the z direction, z is measured just exactly like z would be measured. So it goes from the bottom of this, was the x squared plus y squared, up to the top. But I can't use x's and y squareds because I'm in cylindrical coordinates. So let's see what we can do to change this. We know that x is r cosine theta. We know that y is r sine theta. We know that x squared plus y squared equals r squared. So it looks like I've got a little r squared subtracted here, so this is 50 minus r squared. There's my z. Down here, I've got z equals x squared plus y squared. And so that's just simply going to be z equals r squared. So I'm going to integrate from r squared up to 50 minus r squared. There's my dz. Now, in the xy plane, or the r theta plane, whichever you want to think of, these two shapes intersect right here at this equator. So I need the equation of the equator. We can see it's going to be a circle, and it's also where those two equations match. So let's find out where those intersect. 50 minus r squared equals r squared. 50 equals 2r squared. And so 25 equals r squared. And so r is plus or minus 5, which really we think of as a 5 because if we have a minus r, it's the same as plus r in the other direction. So r equals 5. This is a circle with radius 5. So my r dr ranges from 0, no, not from 0, from the outside of this bead, which is a 1, up to the outside of the circle. Remember, we've got this hole in the middle of radius 1. So from 1 up to 5. There's my r dr. And then for d theta, I have the entire shape. It goes around the whole circle from 0 to 2 pi. There's my setup. And you can see it's not too bad to integrate, so I will not integrate it here. But I will rewrite it to make it look a little bit nicer. I'll move that r up in the middle, and I have dz, dr, d theta. Not too bad to integrate, so I won't take your time. Let's look at spherical coordinates now. Spherical coordinates are really kind of interesting coordinates, and they can help when we have things that shape kind of like spherical. They have symmetry about a point. Okay, so that's what we want to look at there. We don't have an axis of symmetry, but we've got this kind of odd round symmetry somehow. And here's how we take a point and put it into spherical coordinates. So suppose I've got a point right here. It's x squared, x, y, z. That's my point. And here's how I find its coordinates in spherical coordinates. First, I measure from the origin up to that point, and that's rho. My first coordinate in spherical coordinates is called rho. It's the distance from the origin to the point. Then I drop this down and measure out here, and I measure the theta. That's the same theta that would be in cylindrical coordinates. Theta is measured exactly the same way. And then finally I have a third coordinate called phi. And phi measures from the positive z-axis down. So think about phi as like an umbrella. There's the hook of the umbrella. And I measure down in any direction. That's my phi right there. That's how I find that. There's another place to find phi here. I'm going to erase all this so that I can put it in. Phi is also right here. Okay, if you remember from high school algebra, when you have parallel lines, that this angle is equal to that angle. We've got an alternate interior angle thing going on. Okay, so phi is also what I've got marked there. And then to find your coordinates here, you can memorize these, but I really want to show you how this comes about, because if you know how this works, these are really easy to find. This triangle, it's hard to see, but it's sticking out toward you. The base of that triangle is in the xy plane. The base is in the xy plane. And here's what this looks like. There's my rho. Here's the z-axis and my phi. And here's my other phi. So those are both phi. This is my z. And this is my r. If you remember this triangle, you can get anything that you need here. That triangle is the key. Because we know from this picture that r is equal to rho times sine of phi. r is equal to rho times sine of phi. It's the same r in polar coordinates. And that r is equal to rho sine phi from that triangle, that yellow triangle. Well, we can figure out what x is, because in polar coordinates, x is r cosine theta, but r is rho sine phi, so x is now rho sine phi cosine theta from that picture. And we can figure out what r is. From polar coordinates, r is equal to r sine theta, y is equal to r sine theta, but again, r is equal to rho sine phi, so y is equal to rho sine phi sine theta. And then finally in this picture, let me use another color here. In this picture, here's my z value, and z is equal to rho cosine phi in this triangle, just using SOHCAHTOA. So z is equal to rho cosine phi. And I'll just tell you the dv in this system is rho squared sine phi d rho d phi d theta. We can look at that on Tuesday if you want, why that is. But I would just remember it. Rho squared sine phi d rho d phi d theta. I know it's a tricky one to remember. Let's look at an example. So we want to evaluate a triple integral of sine phi, that's my function, over the region 0 less than theta less than or equal to 2 pi, 0 less than phi less than pi over 4, and rho is between 5 and 6 in spherical coordinates. It's not asking us to do this, but I'm going to draw a picture of this. Okay? My theta is between 0 and 2 pi, so this thing is going to go all the way around. My phi is between 0 and pi over 4. So this goes all the way around, and it has an angle here of pi over 4. My rho is between 5 and 6. So if I measure out 5 units, and then measure out 6 units. So this thing, let me erase some of this. Looks like if you took a Dixie cup and cut the bottom of it off. So this is all hollow inside here. There's the inside of that shape. There's that shape. Okay? So let's put this thing together. I'm integrating sine phi. So there's my function. I need a rho squared sine phi d rho d phi d theta. All right. D rho goes from 5 to 6. D phi goes from 0 to pi over 4. D theta goes from 0 to 2 pi. So there's my setup. It's not very hard to set up, but let's look at how we integrate this. I have sine times sine, so I have a sine squared phi times rho squared d rho d phi d theta. That's a rho. The rho's easy to integrate. That's a 1/3 rho cubed. Zero to pi over 4, 0 over 2 pi to 2 pi, d phi, d theta. So this is going to be 6 cubed is 216, 5 cubed is 125. 216 minus 125 is 1. 9, just 91. So this is going to be 91/3 sine squared theta. Sine squared phi. Excuse me, I keep saying that. D phi, d theta. 0 to pi over 4, and 0 to 2 pi. So 91/3 sine squared phi d theta. Let's put another (91/3) sine squared phi d theta. Phi was from 0 to pi over 4. Theta was from 0 to 2 pi. Here's why I wanted to put this integral in. Sine squared phi. We've got a sine squared. I'm going to come back to my double angle formulas. Sine squared theta minus, cosine squared theta. Let me do this right. Cosine of 2 theta equals cosine squared theta minus sine squared theta. I'm going to turn that into a sine squared theta. 1 minus sine squared theta minus another sine squared theta. Cosine of 2 theta is 1 minus 2 sine squared theta. So cosine 2 theta minus 1 over negative 2 is sine squared theta. And that's the same as 1/2 minus 1/2 cosine 2 theta. Although we're using phis here, so I'll change those to phis. And again, I'm not doing a u substitution, so I don't have to change my limits of integration, but this becomes a 1/2 minus 1/2 cosine 2 phi d theta. And now I can integrate that. So this identity is really key. 1/2 phi minus 1/4 sine 2 phi. Phi equals 0 to phi equals pi over 4 d theta. 91/3 0 to 2 pi. So I'm going to have pi over 8 minus 1/4 sine of pi over 2, which is a 1, minus 1/2 phi, 1/2 times 0, minus 1/4 sine of 2 theta, which is still a 0. So now I have 91/3, the integral from 0 to 2 pi of pi over 8 minus 1/4 d theta, which is 2 pi times 91/3 times pi over 8 minus 1/4, whatever that works out to be. So there's that. Okay, moving on. We have one short little topic at the end called double density functions. When you start to take your probability classes, you'll learn more about these. Okay, but here's what you need to have a double density function. The integral over the entire domain of the function must be 1. And what it is the probability that something will happen. So if you want the probability that something happens over some part of the domain, you just take the integral over that part of the domain. Let's look at a real quick example here. So here's a homework question. I have a double density function, sometimes called a joint density function. Okay, and here's my function 3/8x squared over the domain 0 less than x less than 2. So here's my x and my y. Okay, there's a 2, and 0 less than y less than 1. So there's my domain, and this is my function. Outside of that rectangle, that function is a 0. So find the probability that this satisfies x less than 1 and y less than a third. First, though, I'm going to verify that this is a double density function, just to show you how you would do that if it shows up on the homework. So I would need to integrate over the entire domain that function, 3/8 x squared dx dy. In this case, it's easy to set up in rectangular. X goes from 0 to 2 and y goes from 0 to 1 because it's just a rectangle. And if I integrate this, I'm integrating 1/8 x cubed. X goes from 0 to 2 dy, which gives me the integral from 0 to 1 of 1/8 times 8 minus 0 dy, which is the integral from 0 to 1 of 1 dy, which is 1. So yeah, so that's what I need to do, is I need to integrate over its entire domain and check that I get a 1. So once I've got that done, now we can do what the question is asking for. Let me erase this so we've got some more space. So we've verified. Now we're going to find this. So here's what it's asking. It wants the probability that x is less than 1. So there's a 1. And y is less than or equal to a third. So there's a third. So it wants the probability that we're going to land right there. So I just set up my integral. 3/8 x squared dx dy. And x goes from 0 to 1, and y goes from 0 to a third, and then we calculate this out. Which again, I won't do. I won't take your time on this. The previous one was worth doing because it had an integral trick that you may not have known. But this one is very straightforward, so I won't do it.